Okay, this lecture is going to be on higher order ordinary differential equations. So first in the series of a couple of lectures on this topic. The thing that's different about these differential equations is that they contain third order derivatives or higher. Generally with second order differential equations, we're a lot more limited in what solution base we can choose. Third order differential equations are a little more complicated. We're going to make all the assumptions that we made on previous problems, and that is that they have a solution on some interval I. And so all of our theorems of uniqueness, superposition, and linearity that were developed for second order differential equations are all extended for higher order differential equations. So the general form of a differential equation, if it is of nth order, it's going to obtain the nth derivative, which is sometimes written as y with a superscript n, sometimes written as y with a number of apostrophes, sometimes written as d to the n of y dx to the n. So the order is whatever the highest order derivative of the function y is that occurs in the equation. It's called linear if it can be written in standard form. So this is an example of a linear differential equation, and notice that we don't have any of the y's or y's derivatives as squared or cubed. We don't have any nonlinear functions of y present. You can have nonlinear functions of x, but you can't have nonlinear terms of y or its derivatives. So as long as y and its derivatives are in linear form, then the differential equation is linear. Homogeneous means that if we write y and all of its derivatives on the left-hand side of the equation, that there is no corresponding term on the right-hand side of the equation. So this is not equal to some function of x, it's equal to 0. And so once again, for the homogeneous differential equation, a general solution on some interval is a solution of the form of a sum of different independent functions multiplied by some constant. And these functions y1 to yn form what we call a basis or a fundamental system of solutions. So if you have a fourth order differential equation, you could have as many as 4. You'll have as many as 4 linearly independent solutions y1 through 4. Those are a basis set, and the general solution is some linear superposition of those 4 functions. When discussing homogeneous differential equations and we talk about a particular solution, we're basically looking to what happens when we have specific values for those constants. And just as a reminder, the way we get specific values for those constants is by knowing the initial conditions in the problem and applying them and forcing the constants to satisfy the initial conditions. So an initial value problem allows us to solve for those constants, and that gives us the particular solution. If a differential equation is of order n, you've got to have n minus 1 initial conditions or boundary conditions in order to have a complete solution. As an example, here is a third order Euler equation. So here's the differential equation. And then here are the initial conditions. And so you notice we'll have in this particular problem, the initial value x is set at x equal 1. So we have a value for the function y at x equal 1. We have a value for the first derivative at x equal 1. And we have a value for the second derivative at x equal 1. So our standard approach with this kind of equation is to substitute y equals x to the m. So in the first term in this equation, we need the third derivative of y. So we basically differentiate this expression 3 times, which is what gives us this term in the equation. So the m is from the first derivative, the m minus 1 is from the second derivative, the m minus 2 is from the third derivative. And then Notice we have an x cubed term. If we have differentiated x to the m 3 times, we would get an x to the m minus 3. But in this first term, there's an x cubed. So when that x cubed and that x to the m minus 3 multiply each other, we get x to the m. And then the same happens with the second term. We've taken this equation, we've taken its derivative twice, we've substituted it right here for y double prime, we get this term, and so on. So through substitution, we get this equation in x, and this equation has to be equal to 0. Now, since we want this to be true for any value of x, then obviously the trivial solution of x equals 0 is not an option. So if we factor out this x to the m, what has to happen then is we have to force the coefficient equation to go to 0. So this is our equation. We've referred to this before as a characteristic equation. So this is our equation that we need to force to go to 0. So we need to find the roots to this equation. If we find the roots to this equation, then we'll get a basis set of solutions for y. So what I have here is a little bit of MATLAB code that shows how to find the roots of an nth order polynomial. So in this case, I've just defined a variable m, and then in square brackets, in descending order of powers, I have each coefficient. So we can go back to the previous slide, and you see that the coefficients are 1, minus 6, 11, and minus 6. So if we come here, there's our coefficients. If you're missing a power in the equation, and you're going to use MATLAB to solve for the roots of the polynomial, you would need to put a 0 in as a coefficient. If you don't put the 0 in as a placeholder, then MATLAB thinks you don't have that. MATLAB thinks it's of lower order than it actually is. So then you simply use the command roots of m, and MATLAB will output the 3 roots of m. So this means one of the basis solutions is x to the 1, another one is x squared, and another one is x cubed. So our general solution then is c1x plus c2x squared plus c3x cubed. So that's our general solution to this differential equation. So now we want to find the particular solution, and we can do that since we have a set of initial conditions. So first of all, we take y, and then we take its derivative, its first derivative and its second derivative. And these are not negative signs, this is just a dash. So we take 2 derivatives of y, and then remember we have initial conditions at x equal 1. So in this, at x equal 1. So in this first equation, we're going to substitute 1 for x. And we know that the value of y at x equal 1 is 2. So we substitute a 2 for y, and we substitute a 1 for x. For the first derivative, we substitute a 1 for y, and we substitute a 1 for x. And for the third derivative, we substitute a minus 4 for y, second derivative, a minus 4 for y, and a 1 for x. So for each derivative term where we had an initial condition, we're substituting the point x equals 1, and then we're substituting the value of y, y prime, and y double prime respectively. This gives us 3 equations and 3 unknowns, which you can solve through a number of techniques. And solving those 3 equations and 3 unknowns gives us the constants -1, 1, and 2 respectively. And then it's important to put those back in the order in which you solve for them. So C1 is 2, C2 is 1, and C3 is -1. When we do that, we get a particular solution to this differential equation initial value problem. So really very straightforward when we have an Euler type differential equation of higher order.